Last lecture we stopped in here in this slide number 29. So we'll start from here, slide number 29. The characteristics of MSW. MSW is characterized by combination of physical and chemical composition of the waste. So here are some of the physical composition. Identification of the individual components that make up MSW is part of it. Analysis of particle size, moisture content, and density. Some of those we'll discuss more detail. Some of those are just a little bit. So here is individual component of MSW. Typical individual component of MSW, organic compounds, residual waste listed tables 7.3 and 7.4 as shown in the figure below. So in this case, as looks like this is composition of typical MSW. So yard waste 12%, food waste 11, glass, plastic, metals, paper is the highest amount, others, wood. Others means whenever they cannot put in any of the categories, they put it into others. So here are the one organic composition of residual residential refuse. Lignin is the best part, hemicellulose and cellulose. These are highly organic, and this is semicellulose, also organic. Lignin is the more stronger organic part of it, and others if they are not falling under that. Lignin is kind of used as a DNA for like say waste and other things because this is more stable structure there. Okay, particle size. Particle size distribution is very important, and some of the size component materials in solid waste is important for improving the rate of chemical reactions. In other words, smaller particle sizes provide greater surface area and thus more repeat reaction in the microorganism and other cases for the purpose of decomposition. So size distribution is also important consideration in the recovery of materials, for example, with the use of processing equipment such as straw mill, screen, or a magnetic operator. So MSW tends to satisfy vertically when mixed with smaller and denser components migrating into the bottom is the same concept like other cases. Such stratification has implication for efficient combustion of the traveling rate on a boiler or material separation in the MRF, material recovery facility, MRF. So here at the particle size, the calculated by any of the diameter is the L. If it is the other part is very small, and diameter is equal to L plus W plus H by 3, or if it is flat, then L plus W by 2, and then could be done LW to the power 1 by 2 and D equal to LWH to the power 1/3, where D is the diameter, L is the length, W is the width, and the H is the height. So we can do that. So here are the typical sizes, ranges, and typical size of different food waste. 0 to 200, typical is 100 millimeter. So metals like 0 to 200, 100. Clothing and textile is 150. Ashes dust is 25 millimeters. That means 25 millimeter is what, 1 inch, right? MSW contains particles having a wide range of individual sizes. So here another way under such circumstances, particle size is often expressed as mean particle diameter. A number of calculations are possible. Some examples are arithmetic mean and geometric mean and the weighted mean, right? Weighted average, the number mean. These are the one where W is the weight of material in each sieve and size, and M is the total number of particles in each sieve, and N is the number of sieve sizes and in diameters. So here are some of those. This is object per ton. This is mesh size. Looks like falling into this strip is the better particle size distribution for that. And here it is a number individual component given size per ton MSW. So then here is the band. So here is the strip. If it falls under that, most likely falls under that one. The size is percent of total mass with the mesh sizes. So the moisture content is an important part of it. We determine the moisture content same as the soil moisture content. Those who took the geotechnical engineering already might know a little bit. If not, don't worry about it. So we will go through this. The way that we do the moisture content. Initially, we take the waste and we take the weight of it. So and then we dry it like say with 77 degrees Celsius. Certain cases we do 105 degrees Celsius for 24 hours for the other soil cases. If A is the initial mass of sample as delivered and B is the mass after drying, the weight mass moisture content is expressed as MC equal to A minus B over A times 100. So, and this one is A is the weight, right? So weight mass. So that's why this is called the weight basis. And the dry mass moisture content is expressed as follows: A minus B over B times 100. So in geotechnical engineering, always we do this, but in environmental engineering, we need to know this. In geotechnical engineering, they don't even describe the weight mass percentage, weight basis, moisture content weight basis, and dry basis. They are always in terms of the dry basis. So table in the next slide shows typical moisture content values in MSW. So here is the one, different types of waste. This is that shows the range. This is the typical values. So if you don't have any typical values or anything, you can just use those in there. Okay. So we'll be using those in a problem solving that we learned in equation 7172. Definitely we'll be using it. So here is the example 7.1. Estimate the moisture content, both dry and weight basis, of a solid waste sample with the following composition. The composition that I have, it says the food waste 15%, paper 45, cardboard is like 10%, plastic 10, garden trimming 10, wood 5, tin 5. This could probably add up to 100, right? The moisture content in terms of percentage. Food waste looks like 70% moisture and 30% solid. Okay, so these are the moisture content. These are the one came from the table that we saw right from here. Okay, so now let's go ahead and solve the problem. So what I did, I considered the 100 kg of the weight waste. So then food waste, since it is 15%, I assumed 100 kg would be 15 kg and so on. If I add them up, is 100. And moisture content is given. I didn't do anything on that. So now here is the dry mass. Dry mass is like 70% moisture, 30% would be the solid. So 15 times 30%. 30% into this is 1 minus 0.7. I get 4.5 kg here. Similarly, I get 42, 9.5, 9.844, 4.5. If I add them up, I get 78.95 kg, right? So this is the dry weight and this is the weight. So we can consider this in as a this one as a B. So in this case, you see that the weight mass of the waste A equal to 100 kg and B equal to 78.95 kg. Now moisture content in dry basis would be equal to 26.66%. Moisture content on the weight basis, that means is 100 is equal to 21.25%. So this would be less, always the weight basis would be less because A is greater than B. So that's why this would be less than this. As I said, in geotechnical engineering, this is the one always used, and environmental engineering, sometimes we use it. So we'll see when we solve some problem, which one we are going to use and why. So these are the density. This table shows the density of the typical waste. I think the similar waste that we had in the other table that shows the moisture content. Here are the ranges and here are the typical values. These values are in kg per meter cube. This is the density of this, okay? So we'll solve the same problem. So like say food waste and paper is the same problem that we had in 7.1. In this case, we'll estimate the as discarded density of solid waste sample with the composition given below. So these are the same composition. These are the typical density. Where they got it from? I got it from this table, okay? Got it from this table. So now we are going to solve it. So in this case, again, we consider 100 kg of the waste. Then the amount of those components would be 4, 15, 45, and so on. And these are the typical density from the table, previous table. Now we are getting the volume. So volume would be, if I know the like say kg per meter cube and kg, this divided by this will give me the volume. So 15 by 290 will give me 0.0517 meter cube. And everything is the same way we did. So if we add them up together, the total amount of volume would be 1.1066 meter cube, whereas the total mass would be 100. So as discarded means weight basis, right? So if we say a dry basis, then we could get the moisture content out of the moisture content. That means we could use 78.95, right? So in this case, as discarded would be 100 divided by this is equal to 90.3662 kg per meter cube combined. Whereas if we are looking for a density of the dry solid waste, then it could be 78.95 divided by this, so it could be less than that, right? The density per unit volume would be less. So anyway, it could be something I can ask in the exam saying that as discarded. Other than saying as discarded, I could say dry basis, find the density of the dry waste, solid waste. Then you have to do 78 instead of 100, 78.95. Okay, so chemical composition. Chemical composition basically the proximity analysis we do, moisture loss at 105 degrees Celsius for 1 hour. It's a little bit different than the making the moisture content. Volatile matter, VOCs, additional loss on ignition at 950 degrees Celsius. Some cases we do 550 degrees Celsius. Ash residue after burning. So, and the fixed carbon is the remainder of this thing. Then we do the fusing point of ash. You understand the flushing point, fusing point, and boiling point, right? Boiling point is the temperature at which start boiling. Fusing point is start melting, and the flushing point is like say the temperature at which it start burning. So then ultimate analysis, then recent carbon, percent hydrogen of carbon, hydrogen, oxygen, nitrogen, and sulfur, and the ash. Heating value means energy value, BTU, British thermal unit, and other units. So energy content, basically typical data on energy content, and is inert residue for solid waste are reported in table 9.8. So I don't know which table I'm referring to, but I think it's table 1 of the table over there. I think it's coming maybe later on. So energy values may be converted to a dry basis by using the following equations. So this is discarded, like say kilojoule per kg dry, kg per kilojoule discarded times 100 divided by 100 minus moisture content. The corresponding equation on an ash-free dry basis is, so it's very similar except we subtract the percent ash, whatever the percent ash is in there. So I think I didn't show you the energy content, right? Let's see, yeah, here there's a density, but I don't think I have the table for the energy content here. I may need to add it in there. So anyway, so we'll solve this problem. So this the values. Estimate the energy content of solid waste sample. The composition given value looks like the same as before. The energy content are kilojoule per kg. These are the ones, and total energy will find it out. So I use the same way considering 100 kg of solid waste. So food waste is 15. Okay, so that means the kg. Then these are, I got it from the table. As I said, table is not shown there. Probably in the future I'll go and show it in there. And the total energy would be kg, and this one kilojoule per kg. If I multiply this and this, kg cancel out to become kilojoule. So if I do that, I get total, I got 1,474,000 kilojoule for 100 kg of waste. So then we did the as discarded content divided by 100 is equal to per kg. Then the based on the problem 1 weight basis moisture content is 21.5, and energy content on the dry basis, okay, so would be 100 divided by 1 minus moisture content. As I mentioned that, why I'm using the 21 not the 26. 26 was the dry basis, 21 is the weight basis. As I mentioned that the geotechnical engineering always will be using the 26.66%. But in here we are trying to use it to show our conservative estimate. That means if I subtract from here the smaller number, then probably the numerator, I think denominator would be bigger. So denominator would be bigger, that means I'll get a smaller number here, right? So for the conservative estimate, this is my smaller number. That's why I'm going to use the weight basis moisture content here. But if we are looking for a range, then I can use 21% and 26%, then I come up with a range. So from 18,670 kilojoule per kg, we'll get it from here. Or if I use the bigger number, 26.67, it could be 20,000 or something like that. So assuming ash content was 5%, so then if I use the equation, I get 19,932 kilojoule per second per kg. So anyway, we are going to stop here to limit it for 15 minutes. So then we'll continue next one.